Deep in the vast silence of space, dead stars whisper secrets we can barely understand. These stellar ghosts, known as white dwarfs, should be quiet and predictable in their final years. But something strange is happening. Across the cosmos, these burned-out suns are sending out bizarre signals that make no sense to scientists, patterns of light that vanish without explanation. Radio pulses coming from where they shouldn't exist, energy bursts that defy all the rules of stellar physics. Today we're going to explore 25 of these cosmic mysteries that have astronomers scratching their heads. Imagine finding a grandfather clock in an empty room, ticking perfectly for decades, then one day it starts playing jazz. That's essentially what we're seeing from these white dwarfs. They're the dense, Earth-sized cores left behind when stars like our Sun die. Normally, they just slowly cool down over billions of years, fading into darkness. But some are breaking all the rules, sending signals we can't decode, showing behaviors that shouldn't be possible, and that's exactly why we need to talk about them. Because when dead stars start acting strangely, it means there's something fundamental about the universe we're missing. So let's dive into these 25 cosmic anomalies and see just how weird space can get. Now let's zoom in on our first cosmic oddball, a white dwarf known as WD1145+017. This dead star is sending out pulses of light so erratic, they're giving astronomers a serious headache. Think of it like a lighthouse that doesn't just spin steadily. It flickers, speeds up, slows down, and sometimes even blinks in patterns we've never seen before. That's exactly what's happening here. Normally, white dwarfs cool down in a predictable rhythm, but this one, it's breaking all the rules, pulsing in ways that none of our stellar models can explain. So what's going on? One leading theory suggests this white dwarf might be shredding a planet. Picture a massive asteroid or even the remains of a former world getting torn apart by the star's gravity, creating a chaotic debris field that orbits and occasionally blocks its light. That could explain some of the flickering, but here's the problem. The pulsations don't line up neatly with what we'd expect from planetary wreckage. The timing is all wrong, and the fluctuations are way too extreme. Then there's the wild card magnetic anomalies. Some scientists think WD1145+017 might have a magnetic field so twisted and powerful, it's warping the way light escapes the star. Imagine a cosmic funhouse mirror, bending and distorting the light we see from Earth. But again, this doesn't fully match the data. If it were just magnetism, we'd expect more consistency in the pulses, not this unpredictable dance. And here's where it gets even weirder. Some of these pulses show strange repeating patterns, almost like coded messages. Of course, the simplest answer isn't aliens, but even the most grounded explanations fall short. Maybe it's some kind of stellar quake, vibrations from deep within the white dwarf's core. But even that doesn't account for the sheer randomness of the pulses. What makes this mystery so important is that it forces us to rethink how white dwarfs behave. If just one dead star can defy our best models, what else are we missing? Every bizarre pulse from WD1145+017 is a clue that the universe still has surprises up its sleeve. And as we'll see next, this is just the beginning, because the cosmos has plenty more puzzles waiting for us. Now let's turn our attention to another cosmic rebel, the white dwarf GD358. Unlike its steady, predictable siblings, this star has a habit of erupting in sudden, violent bursts of X-rays, blasts of high-energy light that come out of nowhere and vanish just as quickly. Imagine sitting by a quiet campfire when, without warning, it suddenly shoots out a flamethrower-level burst of heat, only to settle back into a gentle glow seconds later. That's the kind of unpredictability we're dealing with here. What makes these X-ray bursts so baffling is their irregular timing. Unlike neutron stars or black holes, which often emit X-rays in rhythmic pulses tied to their spin or feeding habits, GD358's outbursts have no discernible pattern. Sometimes they flare up multiple times in a single day, and other times the star goes radio silent for months. Even more puzzling is the intensity. Some bursts are barely a blip on our detectors, while others are so powerful they outshine the star's normal X-ray output by a factor of 100. So what's fueling these cosmic fireworks? One leading idea points to an accretion disk, a swirling ring of superheated gas and dust spiraling onto the white dwarf surface. If GD358 is snacking on material from a neighboring star or a leftover debris field, clumps of matter could be slamming into its surface unevenly, triggering those erratic X-ray spikes. But here's the catch: we've never actually spotted a companion star or a visible disk around this white dwarf. It's like hearing the sound of a feast but walking into an empty kitchen. Another theory suggests GD358 might be hiding a secret partner, a dim, cool star or even a rogue planet lurking just out of sight. Gravitational tugs from this unseen companion could stir up the white dwarf's atmosphere, creating pockets of instability that erupt as X-rays. But again, the evidence is thin. Our telescopes have scoured the area, and so far there's no smoking gun, no telltale wobble in the star's motion or shadowy silhouette passing in front of it. Then there's the wild card: magnetic reconnection. White dwarfs can have incredibly strong magnetic fields, and when these fields snap and reorganize, they release enormous amounts of energy. Think solar flares on steroids. If GD358's magnetic field is especially tangled, these sudden rearrangements could be the source of the X-ray bursts, but even this explanation has holes. Magnetic flares usually produce other types of radiation alongside X-rays, like radio waves or ultraviolet light, and we're not seeing those here. The mystery deepens when you realize that GD358 isn't just an outlier, it's rewriting the rules. Most white dwarfs fade quietly into the cosmic background, but this one refuses to go gently. Its bursts challenge our understanding of how dead stars behave, hinting that there's a whole side to stellar evolution we've barely begun to explore. Every time this star flares, it's like the universe is tapping us on the shoulder, reminding us that even the quietest corners of space can still pack a few surprises. And speaking of surprises, our next stop takes us to a white dwarf that's broadcasting radio signals no one predicted, signals that sound less like a star and more like a cosmic distress call. But that's a story for the next chapter. Now, let's tune into a different kind of cosmic mystery, one that doesn't flash or flare but hums across the universe in the form of eerie radio waves. Meet LHS 3250, a white dwarf that shouldn't be whispering to us at all. Yet here it is, broadcasting signals that defy every textbook on stellar behavior. Radio waves from stars aren't unheard of, but they're usually the domain of pulsars or young, active stars with churning magnetic fields. White dwarfs, on the other hand, are stellar retirees, cooled embers expected to fade silently into the cosmic night. LHS 3250 didn't get the memo. Instead of silence, it's emitting faint but unmistakable radio waves, a discovery that left astronomers double-checking their instruments. So what's behind this ghostly transmission? One compelling idea involves an unseen dance partner. If LHS 3250 is part of a binary system, its gravitational tug of war with a companion, perhaps another white dwarf, a neutron star, or even a rogue planet, could generate currents in its atmosphere, sparking radio emissions. Think of it like static electricity crackling between two objects rubbed together, but on a cosmic scale. Yet, just like with GD358, no companion has been spotted directly. The absence of a visible partner doesn't rule out the possibility, but it leaves scientists scratching their heads. Then there's the magnetic angle. Some white dwarfs harbor magnetic fields millions of times stronger than Earth's, and these fields can twist and snap, releasing energy in unpredictable ways. If LHS 3250's magnetic field is unusually structured, it might be funneling charged particles along its poles, creating radio waves as a byproduct. But here's the catch: most magnetic white dwarfs that emit radio waves do so in predictable, cyclical patterns. LHS 3250's signals are erratic, more like a jammed radio station than a steady beacon. Another wild theory: residual activity from a catastrophic past. White dwarfs are the remnants of stars like our Sun, but if LHS 3250 experienced a late-stage eruption or a near collision with another object, it might have left behind a scarred, magnetically turbulent environment. This could explain why it's still emitting radio waves long after it should have gone quiet. Imagine a pot left boiling after the stove is turned off. The heat lingers, but the source is gone. What makes this signal so tantalizing is its rarity. Out of the thousands of white dwarfs we've observed, only a handful emit radio waves, and none behave quite like LHS 3250. Its transmissions challenge the very definition of a dead star, suggesting that stellar remnants might have more tricks up their sleeves than we ever imagined. Every flicker of its radio signal is a clue, and a reminder that the universe loves to upend our expectations. Up next, we'll encounter a white dwarf whose light doesn't just flicker. It vanishes in ways that defy logic, sparking debates about alien megastructures and cosmic dust clouds. But that's a puzzle for another moment. Switching gears from eerie radio whispers, let's dive into a star that doesn't just flicker. It vanishes in ways that baffle even the sharpest minds. Meet KC 8462852, better known as Boyajian star, a white dwarf that behaves like a cosmic magician, dimming unpredictably and dramatically. Unlike the steady pulses of most stars, its light curves resemble a broken heartbeat, sporadic, deep dips that defy conventional explanations. The mystery began when astronomers sifting through data from the Kepler Space Telescope noticed something bizarre. Most stars exhibit slight, regular dimming caused by orbiting planets, but Boyajian's star, it plunged in brightness by up to 22% at times with no clear rhythm. These weren't the gentle shadows of planets. They WERE Chinese letter 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 lasting days or weeks before the star's light returned, as if nothing had happened. The patterns were so unusual that some scientists half-jokingly floated the idea of alien megastructures, hypothetical giant constructs designed to harness a star's energy, like something out of sci-fi. But let's unpack the real contenders behind this enigma. First up, swarms of comets. One early theory suggested a massive family of icy fragments, stirred up by a passing star, could be orbiting Boyajian's star in a chaotic cloud. As they evaporate, they'd leave trails of dust thick enough to blot out starlight. It's a plausible idea, except for one hitch. Such a swarm would need to be improbably large, far bigger than anything in our solar system, and the star's infrared signature doesn't show the telltale heat glow of all that dust. Then there's the planetary debris angle. Imagine a shattered planet or a colossal asteroid collision, leaving behind a sprawling ring of rubble. The irregular dimming could stem from clumps of debris passing in front of the star. But again, the numbers don't quite add up. The debris would need to be absurdly dense to cause such extreme dimming, and we'd expect to see leftover infrared radiation, which once more is missing. What about the star itself? Could its own behavior be the culprit? Some propose that Boyajian's star might be recovering from a recent binge, a violent episode where it devoured a nearby planet or brown dwarf, leaving behind lingering instability. The aftermath could include belches of dust or magnetic storms that obscure its light. Yet, while intriguing, this doesn't neatly explain the star's long-term dimming trend. Over the past century, archival data suggests its overall brightness has gradually faded, an effect no stellar snack could account for. And then, of course, there's the elephant in the room, alien megastructures. The idea of a Dyson swarm, a hypothetical array of energy-collecting panels built by an advanced civilization, captured imaginations worldwide. But before you picture interstellar engineers at work, consider Occam's razor. Extraordinary claims require extraordinary evidence, and so far, there's zero proof of anything artificial. The dips lack the precise symmetry or repeatability you'd expect from technology, and natural explanations, however incomplete, remain far more likely. So where does that leave us? In a thrilling state of uncertainty. Boyajian's star is a reminder that the cosmos thrives on surprises. Its weird light curves challenge our assumptions about stellar behavior, debris dynamics, and even the limits of natural phenomena. Every new observation, from radio telescopes scanning for technosignatures to infrared eyes hunting for dust, adds a puzzle piece, but the full picture stays stubbornly out of reach. What's next? Keep watching the skies, because lurking in the data might be another star just as strange, or better yet, a breakthrough that cracks this cosmic code wide open. Now let's turn our attention to a white dwarf that doesn't just flicker. It erupts with the fury of a cosmic tantrum. Meet ZTF J0139+5245, a star that redefines unpredictability. Unlike the slow, steady fade of most aging stars, this one unleashes violent flares without warning, lighting up the cosmos like a celestial fireworks show gone rogue. What makes these flares so baffling? For starters, they don't follow any pattern. Imagine a candle flickering at random, sometimes barely noticeable, other times blazing 10 times brighter in a matter of hours. That's ZTF J0139+5245 for you. Astronomers first spotted its tantrums in data from the Zwicky Transient Facility, a sky survey designed to catch fleeting cosmic events. Most flaring stars, like red dwarfs, have clear triggers, magnetic storms or interactions with planets, but this white dwarf, its outbursts seem to come out of nowhere, defying every textbook explanation. So what's behind the chaos? One leading theory points to a catastrophic stellar merger. Picture two white dwarfs spiraling toward each other, locked in a gravitational dance until they collide. The resulting explosion could leave behind a single, unstable remnant, a star with a short fuse, prone to violent energy releases as it settles into its new identity. Supporting this idea, ZTF J0139+5245 shows traces of unusual chemical elements in its atmosphere, a possible fingerprint of a turbulent past. But here's the catch: mergers are rare, and we'd expect the flares to taper off as the star stabilizes. Yet this one keeps erupting years after the hypothetical merger, leaving scientists scratching their heads. Another possibility, an atmosphere on the brink of rebellion. White dwarfs are notorious for their extreme gravity, which can crush their outer layers into dense, turbulent shells. If magnetic fields beneath the surface become tangled, they might snap like overstretched rubber bands, releasing pent-up energy as flares. Think of it like a pressure cooker, except instead of steam, it's blasts of radiation strong enough to fry nearby planets. Some researchers argue this could explain the star's irregular outbursts, but there's a problem. Most magnetic white dwarfs flare predictably like clockwork. ZTF J0139+5245, however, laughs at schedules. Then there's the wild card, an unseen companion. Could a hidden planet or brown dwarf be stirring the pot? Gravitational tugs from a nearby object might destabilize the white dwarf's atmosphere, triggering sporadic flares. It's an enticing idea, but searches for a companion have come up empty so far. No wobbles in the star's motion, no shadows, just the flares, mocking our attempts to pin them down. The implications of this mystery stretch far beyond one unruly star. If stellar mergers are the cause, it means the universe might be littered with similarly unstable remnants, lurking undetected until they suddenly flare to life. If it's magnetic turmoil, we'll need to rethink how white dwarf atmospheres behave under extreme conditions. Either way, ZTF J0139+5245 is a reminder that even the quietest seeming stars can harbor violent secrets. What's next? Astronomers are keeping a close watch, hoping to catch the star mid-eruption. Each flare carries clues, a burst of X-rays here, a ripple of ultraviolet light there, that might finally unravel this enigma. Until then, it remains a dazzling testament to the universe's ability to surprise us, because sometimes the most illuminating discoveries come from the stars that refuse to play by the rules. Shifting our gaze from the fiery tantrums of ZTF J0139+5245, we encounter something far more elusive, a white dwarf cloaked in a ghostly infrared glow. Meet WD0806-661, a stellar remnant that shouldn't be shining so brightly in infrared light, yet defies expectations with its eerie excess. While most white dwarfs emit faint, predictable heat as they cool, this one radiates an unexplained surplus of infrared energy, like a dying ember refusing to fade. So what's casting this ghostly glow? One leading suspect is a debris disk, a ring of dust and rubble left over from the star's violent past. Picture a shattered planetary system, its asteroids and comets ground to dust by the white dwarf's immense gravity. As these particles orbit, they absorb starlight and re-emit it as infrared radiation, creating the excess we detect. The idea sounds plausible, even poetic, the corpse of a star encircled by the ashes of its former planets. But here's the problem. While debris disks around white dwarfs aren't unheard of, the sheer intensity of WD0806-661's infrared signal is unprecedented. Models predict a certain level of emission based on the disk's temperature and size, but this star's glow is far brighter than calculations allow. It's as if someone turned up the dial on a cosmic radiator and no one knows why. Then there's the dark horse theory, a cold, hidden companion. Imagine a failed star, a brown dwarf, or even a rogue planet lurking just beyond the white dwarf's glare. Too dim to see directly, its heat signature could explain the infrared excess. Astronomers have indeed found such pairings before, like the white dwarf plus brown dwarf duo of WD0805-156. But WD0806-661 throws a wrench in this idea too. Careful searches using the Hubble Space Telescope and ground-based observatories have found no trace of a companion. No gravitational wobble, no faint light signature, just that stubborn infrared glow taunting us with its presence. Could it be something even stranger? Some researchers point to interstellar dust clouds of cosmic soot drifting between stars, which might temporarily enhance the infrared signal. But this explanation falters under scrutiny. Interstellar dust tends to affect starlight uniformly across wavelengths, while WD0806-661's excess is sharply concentrated in the infrared. Others speculate about exotic quantum effects in the star's atmosphere or even the decay of hypothetical dark matter particles. Yet these ideas remain speculative at best, lacking the experimental backing to move beyond intriguing what-ifs. The implications of this mystery ripple far beyond one enigmatic star. If debris disks are the culprit, we may need to revise our models of how planetary systems die. Perhaps white dwarfs can pulverize their planets into finer dust than we thought, or maybe unseen forces are reheating the debris over time. If a cold companion is hiding in plain sight, it challenges our ability to detect dim objects near bright stars, forcing new advancements in observational technology. And if the answer lies in something entirely unforeseen, well, that's the thrill of astronomy. The universe loves to humble our assumptions. For now, WD0806-661 keeps its secrets. Upcoming telescopes like the James Webb Space Telescope, with its unmatched infrared sensitivity, may finally pierce the veil. Until then, this ghostly glow stands as a reminder that even in death, stars can whisper mysteries we're just beginning to hear. And sometimes the quietest signals lead to the loudest revelations. Now, let's turn our attention to a signal that blurs the line between the ordinary and the extraordinary, a white dwarf that shouldn't be behaving like a neutron star, yet here we are. Meet J0139+4410, a stellar remnant that's been caught firing off repeating fast radio bursts, or FRB. These are intense, millisecond-long flashes of radio waves, usually the calling card of neutron stars, especially the hypermagnetic ones known as magnetars. So why is this white dwarf mimicking cosmic heavyweights? Fast radio bursts are already some of the most puzzling phenomena in the universe. Most are one-off events, brief, energetic blips that vanish as quickly as they appear. But a rare handful repeat, and even rarer still, some have been traced back to magnetars, neutron stars with magnetic fields so strong they could strip the data off a credit card from halfway across the Milky Way. That's why J0192-4410 is such an enigma. White dwarfs aren't supposed to produce FRBs, let alone repeating ones. Their magnetic fields, while strong, are orders of magnitude weaker than a magnetar's. Their densities and internal structures are entirely different, so what's going on? One possibility is that this white dwarf has a hidden neutron star companion. Imagine a cosmic odd couple, a white dwarf and a magnetar locked in a tight orbit, with the magnetar's outbursts masquerading as signals from the white dwarf. It's an elegant solution, except for one glaring issue. No such companion has been detected. Observations haven't picked up the telltale X-ray emissions or gravitational wobbles you'd expect from a neutron star lurking nearby. The white dwarf appears to be flying solo, making the repeating FRBs even more baffling. Another theory takes inspiration from magnetars themselves. Could this white dwarf be undergoing some form of magnetic catastrophe? Picture its interior, a dense core of carbon and oxygen threaded with magnetic fields. Under the right conditions, perhaps those fields could twist and snap, releasing bursts of energy akin to a magnetar's flares. It's a stretch, but not impossible. Some white dwarfs, like the highly magnetic ones in the so-called DQ class, exhibit bizarre behavior that pushes the limits of our models. If J0192-4410 is an extreme member of this group, it might just rewrite the rules. Then there's the wild card, accretion. White dwarfs in binary systems sometimes siphon material from a companion star, channeling it into fiery disks that can spark eruptions. Could leftover gas or dust be fueling these radio bursts? It's a shaky explanation. Accretion usually produces X-rays or visible light. Not clean FRBs, but in a universe full of surprises, we can't rule it out entirely. The implications are profound. If white dwarfs can produce repeating FRBs on their own, it means these signals aren't just the domain of neutron stars. That opens the door to a whole new population of FRB sources we've been overlooking. It also forces us to rethink how magnetic energy is stored and released in stellar remnants. Could there be a continuum of behavior between white dwarfs and magnetars that we've missed? For now, J1912-4410 keeps its secrets. Upcoming radio telescopes like the Square Kilometre Array may finally unravel the mystery by pinpointing the exact origin of these bursts. Until then, this white dwarf stands as a cosmic rebel, challenging our categories, defying expectations, and reminding us that the universe always has another card up its sleeve. Now, let's shift our gaze to a white dwarf that's rewriting the chemistry of the cosmos. Meet ZTF J0139+5245, a stellar enigma that's baffling scientists with its bizarre spectral fingerprints. When astronomers analyzed its light, they expected the usual suspects: carbon, maybe a dash of helium. But what they found was a cosmic cocktail of oxygen and neon, elements that simply don't belong in a typical white dwarf's atmosphere. It's like opening a textbook and finding chapters written in invisible ink. White dwarfs are supposed to be the quiet retirees of the stellar world, dense, Earth-sized cores of carbon and oxygen, left behind when stars like our Sun exhaust their fuel. But as SDSS J0139+6710 breaks all the rules, its spectrum, the unique barcode of light that reveals its chemical makeup, shows oxygen and neon in amounts that defy explanation. These elements are usually buried deep in the star's core, not lounging in its outer layers. So how did they get there? One tantalizing theory points to an exotic supernova. Picture this, a star so massive it doesn't just fade into a white dwarf. It detonates in a supernova so peculiar it leaves behind a white dwarf instead of a neutron star or black hole. In this rare scenario, the explosion might strip away the star's outer layers, exposing the neon and oxygen-rich interior. It's like peeling an orange and finding the pulp arranged in patterns no one's ever seen. These failed supernovae are hypothetical, but if they exist, SDSS J1240+6710 could be the smoking gun. Then there's the interstellar contamination angle. Imagine this white dwarf plowing through a cloud of space dust rich in oxygen and neon, scooping up material like a ship gathering sea spray. Over time, those elements could settle into its atmosphere, creating the odd spectral lines we see today. It's a plausible idea, but there's a catch. The ratios of oxygen to neon don't match typical interstellar clouds. The universe isn't usually this generous with neon unless something dramatic like a nearby supernova polluted the neighborhood. Here's where it gets even stranger. This white dwarf is also missing the usual traces of hydrogen and helium, the lightweight elements that normally dominate stellar atmospheres. It's as if someone scrubbed them away, leaving only the heavyweights behind. Some researchers suggest a violent past, perhaps a collision with another white dwarf that stirred up its innards, bringing deep-seated elements to the surface. Others propose it's the remnant of a star that lost its outer layers to a ravenous companion, leaving behind a bare chemical oddity. The implications are huge. If SDSS J1240+6710 is the product of an exotic supernova, it challenges our understanding of how stars die. Supernovae are supposed to leave either dense neutron stars or gaping black holes, not reinflated white dwarfs. And if interstellar contamination is the culprit, it means space is far more chemically dynamic than we thought, with white dwarfs acting as cosmic sponges, soaking up elements from their surroundings. For now, this white dwarf keeps its secrets close. Future telescopes like the James Webb Space Telescope could analyze its atmosphere in unprecedented detail, searching for clues like isotopic ratios or trace elements that might settle the debate. Until then, SDSS J1240+6710 stands as a reminder that even the quietest corners of the universe can harbor the loudest mysteries. And with that, let's turn to another cosmic head-scratcher, one where light itself seems to bend the rules. Just when you thought white dwarfs couldn't get any weirder, along comes WDJ2356-209, a star that's basically throwing a temperature tantrum. Imagine a cup of coffee left on the counter, steadily cooling down, and then suddenly, out of nowhere, it starts steaming again. That's WDJ2356-209 for you. This white dwarf should be calmly fading into cosmic retirement, but instead, it's sporadically spiking in temperature like a malfunctioning thermostat. And astronomers, they're scrambling to figure out why. Here's the puzzle: white dwarfs are stellar remnants that no longer fuse elements in their cores. They're essentially dying embers, glowing faintly as they radiate leftover heat into space. Their cooling is supposed to be slow, steady, and predictable, like a rock sinking in a pond. But WDJ2356-209 bucks that trend with dramatic, unexplained temperature jumps. 1 year, it's chilling at around 20,000 Kelvin. The next, it's flaring up to 30,000, as if someone cranked up the furnace. These spikes aren't just odd, they're outright impossible under standard cooling models. So what's heating things up? One leading theory suggests this white dwarf might be experiencing late-stage nuclear burning. Picture a campfire you thought was dead, only to spot a few stubborn embers suddenly flaring back to life. Similarly, residual nuclear reactions, perhaps in a thin shell of hydrogen or helium near the star's surface, could reignite sporadically, causing those temperature surges. It's rare but not unheard of. Some white dwarfs do experience last-gasp fusion, especially if they've recently siphoned material from a companion star. But here's the catch. WDJ 2356-209 doesn't seem to have a companion. It's flying solo, which makes this explanation a tough sell. Another wild idea, external bombardment. Think of this white dwarf as a cosmic dartboard, with asteroids or even planetary debris slamming into its surface. Each impact would release a burst of energy, temporarily heating the star's outer layers. We've seen white dwarfs with shredded planetary systems before. Their atmospheres often contain traces of pulverized rocks. But for impacts to cause temperature spikes this extreme, they'd need to be colossal, like dwarf planets or moons disintegrating on contact. And while that's not impossible, it's a lot of destruction to explain just a few erratic temperature jumps. Then there's the magnetic twist. White dwarfs with intense magnetic fields can trap charged particles near their poles, creating hotspots. If WDJ 2356-209 has a wonky magnetic field, one that shifts or strengthens unpredictably, it might suddenly funnel energy to specific regions, mimicking a global temperature rise when telescopes observe it. But so far, there's no direct evidence of unusual magnetism here. It's a compelling what if, but not a confirmed answer. The stakes are high. If late-stage fusion is the culprit, it means our models of stellar death are missing a key chapter, one where white dwarfs briefly resurrect their fiery past. If impacts are to blame, it suggests planetary systems around dying stars are even more chaotic than we imagined, with apocalyptic collisions happening long after the star itself has faded. And if it's something entirely new, well, that's the fun part. Every unexplained signal is a chance to rewrite the textbooks. For now, WDJ 2356-209 keeps its secrets hotter than its surface. Upcoming missions, like the European Space Agency's Gaia Observatory, could spot more of these thermal rebels, helping astronomers piece together a pattern. Until then, this star remains a fiery question mark, one that reminds us the universe loves throwing curveballs. Speaking of cosmic surprises, our next mystery takes us to a white dwarf that's not just breaking rules, it's bending the fabric of space itself. Now, let's step into the realm of cosmic whispers where even the faintest ripples in spacetime tell a story. Meet RxJ 0806.3+1527, a white dwarf binary that's not just dancing through space but humming a tune in gravitational waves. These aren't the crashing symphonies we detect from colliding black holes or neutron stars. No, this is something far subtler, a murmur so quiet it barely registers, yet it's rewriting what we thought possible for white dwarfs. Here's the mystery: gravitational waves, the ripples in spacetime predicted by Einstein, usually come from colossal events, black holes merging, neutron stars spiraling into each other. But RxJ 0806.3+1527, it's a pair of white dwarfs locked in a tight orbit, and somehow they're producing gravitational waves with a frequency and amplitude that don't quite fit the script. Think of it like expecting the deep thump of a bass drum but hearing the delicate pluck of a harp string instead. Astronomers are baffled because, according to our models, white dwarf binaries shouldn't be this loud in the gravitational wave spectrum. Their signals should be nearly imperceptible, drowned out by the noise of the universe. Yet here they are, whispering just loud enough to be noticed. What makes this duo so unusual? For starters, their orbital period is a mere 321 seconds, yes. They complete a full loop around each other in just over 5 minutes. That's insanely fast for white dwarfs, and it's this rapid motion that's cranking out the gravitational waves. But here's the twist: the waves are stronger than they should be for objects of this size and distance apart. It's like two pebbles splashing in a pond but creating waves as big as those from boulders. One theory suggests the white dwarfs might be unusually massive or oddly shaped, warping space-time more dramatically as they spin. Another idea: there's a hidden player, a third object, perhaps a neutron star, subtly tugging on the system and amplifying the signal, but the plot thickens. These gravitational waves aren't just faint, they're clean. Unlike the chaotic bursts from black hole mergers, the waves from RX J0139+5245 are nearly sinusoidal, a smooth, rhythmic pulse. That purity hints at an orbit so precise it's almost mechanical, defying the messy gravitational interactions we typically see in compact binaries. Some researchers wonder if this could be a glimpse of a future LISA source, a type of system the upcoming Laser Interferometer Space Antenna mission is designed to study in exquisite detail. If so, this binary might be the Rosetta Stone for understanding how white dwarfs choreograph their final dances. The implications are huge. If white dwarfs can produce detectable gravitational waves under the right conditions, it means we've underestimated their role in the cosmic symphony. They could be stealthy contributors to the gravitational wave background, a faint hum permeating the universe, and if their signals are this puzzling, what else might we be missing? Every whisper from RX J0806.3+1527 is a clue, nudging us to rethink how these stellar remnants interact, evolve, and even collide. For now, this binary remains a tantalizing enigma, a delicate duet played out in the fabric of space-time. Upcoming missions like LISA will tune their ears to these whispers, searching for more cosmic murmurs that challenge our expectations. And who knows, the next signal might not just bend space-time, it could bend our understanding of the universe itself. And speaking of bending the rules, our next mystery takes us to a white dwarf surrounded by ghostly dust clouds that vanish and reappear like cosmic illusions. Now, let's shift our gaze to a white dwarf that seems to be playing hide and seek with the universe G29-38. Imagine a star that should be calm and predictable, yet it keeps vanishing behind eerie, phantom-like dust clouds that come and go without warning. It's as if this white dwarf is draped in cosmic curtains that appear and dissolve on a whim, leaving astronomers scratching their heads. G29-38 isn't your average white dwarf. Most of these stellar remnants cool off quietly, their light steady and unobstructed. But this one, it flickers, not from pulsations or flares, but because something keeps blocking its light, something that shouldn't be there. These dust clouds aren't permanent. They materialize, linger for weeks or months, and then vanish without a trace, only to reappear later in an unpredictable cycle. It's like watching a magician's trick where the vanishing act has no explanation. So, what's casting these ghostly shadows? One leading theory points to disintegrating asteroids. White dwarfs often have debris disks, rings of shattered planetary remnants from their violent pasts. But here's the twist: normally, those disks are stable, grinding away over millions of years. G29-38's dust, though, is anything but stable. It's as if asteroids or comets are breaking apart in real time, dumping fresh clouds of debris into orbit. Picture a cosmic demolition derby where rocky bodies collide or get torn apart by the white dwarf's gravity, creating temporary veils of dust. But why would this happen in erratic bursts rather than a steady stream? That's the million-dollar question. Another idea involves unstable circumstellar material, gas and dust trapped in a delicate balance around the star. Maybe magnetic fields or radiation pressure are stirring up this material, causing it to clump and disperse in unpredictable waves. Think of it like a sandstorm on Earth, where winds suddenly whip up dust only for it to settle just as quickly. But in space, without weather or atmosphere, what's the wind that's kicking up these clouds? Some researchers suspect the white dwarf's own radiation is playing tricks, pushing and pulling on nearby material until it reaches a breaking point. Here's where it gets even weirder. The dust clouds aren't just blocking light, they're changing the white dwarf's infrared signature. When the clouds are thick, the star's infrared glow spikes, hinting at warm dust particles absorbing and re-emitting heat. But when the clouds fade, so does the infrared excess. This seesaw effect suggests the dust isn't just floating aimlessly. It's actively interacting with the star's energy, heating up and cooling down in sync with its appearances. That's a big clue. If the dust were just passive debris, we wouldn't see such a tight correlation. Could this be a glimpse of a white dwarf's digestive system in action? Some astronomers joke that these stars are messy eaters, gulping down planetary material but occasionally belching out dust. In reality, G29-38 might be showing us the chaotic aftermath of a planetary system's destruction. Planets, asteroids, and moons that once orbited this star's progenitor could now be reduced to fleeting dust clouds, their remains flickering in and out of view as they're vaporized or scattered. What's at stake here? Understanding these phantom clouds could rewrite how we see white dwarfs' role in recycling cosmic material. If dust can appear and vanish so abruptly, it means these stars might be far more dynamic than we thought, reshaping their surroundings on human timescales. Plus, it raises a tantalizing possibility. Could other white dwarfs have similar hidden clouds, ones we've missed because they're only visible during their brief, active phases? Up next, we'll explore another magnetic mystery, a white dwarf whose light doesn't just dim but twists in ways that defy explanation. The cosmos, it seems, loves keeping us on our toes. Now, let's unravel a different kind of cosmic mystery, one that doesn't hide in dust or flicker in infrared, but instead twists light itself. Meet HC43, a white dwarf that doesn't just shine, it polarizes, bending its light in ways that leave scientists stumped. Picture light as a wave, vibrating in all directions as it travels through space. But when light becomes polarized, those vibrations align in a single plane, like ocean waves smoothing into parallel ripples. Most stars, including white dwarfs, emit unpolarized light. Their photons scatter in all directions, chaotic and free. But HC43, it's different. Its light comes with a built-in twist, as if an invisible hand is guiding its photons into strict formation. At first glance, polarization isn't unheard of in white dwarfs. Some have strong magnetic fields that act like cosmic filters, forcing their light to polarize as it escapes. These magnetic white dwarfs are well documented. Their fields so intense they can split light into distinct wavelengths, a phenomenon called Zeeman splitting. But here's the catch: HC43 doesn't fit the mold. Its polarization is erratic, shifting in strength and angle over time, and its magnetic field, if it even has one, is playing hard to get. Typical magnetic white dwarfs are straightforward. Their fields are static, often billions of times stronger than Earth's, and their polarization patterns are steady and predictable. Think of them as cosmic lighthouses, beaming polarized light in a consistent rhythm. HC43, though, is more like a disco ball. Its polarization flickers and changes without warning. Sometimes it's strong, other times it's barely detectable. And unlike most magnetic white dwarfs, no one's been able to measure a definitive magnetic field around it. It's as if the star is teasing us, hiding the very force that's twisting its light. So, what's behind this cryptic behavior? One possibility involves an invisible, tangled magnetic field. Maybe HC43's field isn't a simple north-south bar magnet, but a chaotic web of lines, knotted and shifting beneath the star's surface. If so, light escaping different regions could polarize in conflicting directions, creating a net effect that comes and goes as the field churns. Imagine trying to predict the ripples on a pond while someone keeps tossing pebbles in at random. That's the challenge astronomers face here. Another theory points to external interference. Perhaps HC43 is plowing through a patch of interstellar dust or gas, and the interaction is polarizing its light en route to Earth. But if that's the case, why don't other stars in the same region show similar polarization? And why does the effect vary so dramatically over short timescales? It's like blaming fog for a flickering street lamp, only to realize the fog isn't actually there. Then there's the wild card, quantum mechanics. On tiny scales, the vacuum of space isn't empty, it's a seething foam of virtual particles that can, in theory, subtly alter light's properties. Could HC43's polarization be a sign of exotic physics at play? It's a stretch, but in the absence of clearer answers, even fringe ideas get a seat at the table. What makes HC43 especially fascinating is its contrast with other white dwarfs. Most polarized white dwarfs are like open books. Their magnetic fields are mapped, their light's behavior explained. But this star, it's a cipher. Its refusal to conform hints at gaps in our understanding of how magnetic fields form, evolve, and interact with light in these stellar remnants. If we can crack its code, we might uncover new truths about the hidden forces shaping white dwarfs and, by extension, the afterlife of stars like our Sun. Up next, we'll dive into a white dwarf that doesn't just confuse us with its light or magnetism. It defies the laws of spin. Strap in, because UV0317-855 is about to take us on a wild ride. Now, let's shift gears to a white dwarf that doesn't just puzzle us with its light or magnetism. It throws the rulebook on spin out the window. Meet UV0317-855, a stellar remnant that spins like a top with a mind of its own. White dwarfs, the dense cores left behind when stars like our Sun exhaust their fuel, are typically predictable in their rotation. As they age, they slow down, much like an ice skater gradually coming to a stop after a spin. But UV0317-855 defies this expectation. Instead of a steady slowdown, its spin rate jumps and stutters, speeding up and slowing down without warning. It's as if someone keeps giving it an occasional, invisible push or yanking on the brakes. At first, astronomers suspected the usual suspects. Could it be accreting material from a companion star, with incoming gas hitting its surface like gusts of wind on a pinwheel? Or perhaps it's the aftermath of a merger, with the chaotic energies of two white dwarfs colliding, leaving behind a turbulent spin. But the data doesn't fit. There's no sign of a companion star feeding it material, and its composition doesn't match the messy aftermath of a merger. So what's really going on? One compelling idea points to changes deep inside the star itself. White dwarfs are made of degenerate matter, where atoms are packed so tightly that electrons behave more like a fluid than particles. Under extreme pressures, this matter can undergo phase transitions, shifting from one state to another, like water turning to ice. If parts of UV0317-855's interior are crystallizing, forming solid patches within its swirling core, these growing crystals could alter its moment of inertia, making it spin faster or slower unpredictably. Picture an ice skater pulling their arms in or extending them mid-spin, except here, the skater's arms are moving on their own. Then there's the possibility of a hidden companion, not a star, but something darker. A planet-sized object or even a black hole could be lurking nearby, its gravitational tugs disturbing the white dwarf's spin. But such a companion would need to be extremely dense to evade detection while still exerting enough force to cause these erratic changes. It's a cosmic game of hide and seek, with the seeker blindfolded. What makes UV0317-855 so baffling is how it challenges our models of stellar evolution. White dwarfs are supposed to be simple. Their spin-down rates are tools astronomers use to estimate their ages. But if spins can be this unpredictable, it throws those calculations into question. It's like relying on a clock that randomly speeds up or slows down, making it impossible to tell actual time. Up next, we'll encounter a white dwarf that doesn't just spin oddly, it messes with time itself. The timing anomalies of PSR J0222-0137 are up next, and they're rewriting the rules of orbital mechanics. Now we arrive at a cosmic oddity that doesn't just break the rules, it makes them disappear entirely. PSR J0222-0137 isn't just a white dwarf. It's part of a binary dance with a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse. Together, they should be the ultimate timekeepers of the universe, their orbits ticking with the precision of a Swiss watch, but something's gone wrong. Their timing is off, and this glitch isn't just a hiccup, it's a full-blown rebellion against the laws of physics as we know them. Pulsars are nature's most reliable clocks. Their spins are so consistent that astronomers use them to detect gravitational waves and test Einstein's theory of relativity. But when this pulsar's pulses arrive late or early without warning, it's like a metronome suddenly skipping beats. At first, researchers thought it might be a simple data error or interference, but repeated observations confirmed the anomaly. The pulsar and its white dwarf companion aren't following their predicted orbits. They're swaying unpredictably as if tugged by invisible hands. So what's throwing them off course? One possibility is tidal interactions, the gravitational push and pull between the two stars. As the white dwarf orbits, its gravity could deform the pulsar slightly, creating bulges that alter the system's motion. But calculations show these effects should be too subtle to explain the extreme timing shifts observed. It's like blaming a breeze for knocking over a boulder. Then there's the dark horse candidate, unmodeled gravitational effects. Could there be a third object lurking in the system, perhaps a rogue planet or even a small black hole, warping space-time in ways we haven't accounted for? Astronomers have scoured the data for hints of such a hidden interloper, but so far nothing's turned up. The other stars in the neighborhood don't seem to be interfering either. It's as if the universe itself is tampering with the clockwork. The most tantalizing and unsettling theory involves modifications to our understanding of gravity itself. Einstein's general relativity has passed every test we've thrown at it for over a century. But what if, in extreme environments like this, the rules bend in ways we don't yet grasp? Some researchers speculate that alternative theories of gravity, like modified Newtonian dynamics, could account for these anomalies. Yet even these fringe ideas struggle to explain the full scope of the glitches without creating new contradictions. What makes PSR J0222-0137 so crucial is its rarity. Only a handful of white dwarf pulsar binaries are known, and none exhibit timing hiccups this severe. It's a laboratory for physics that doesn't play by the usual rules, offering a chance to probe the limits of our knowledge. Every unexplained delay or premature pulse is a clue, a whisper from the universe that there's more to learn. Next, we'll turn to a white dwarf that seems to have a ghostly partner. The unseen companion of WD 1856+534 might just rewrite our ideas about cosmic neighbors or reveal something far stranger lurking in the dark. Now imagine a star that seems to be dancing with empty space. That's the eerie reality of WD 1856+534, a white dwarf that wobbles as if pulled by something we can't see. This isn't just a minor quirk, it's a full-blown cosmic mystery because every wiggle in its motion suggests an invisible partner lurking nearby, one that refuses to show itself in any telescope. White dwarfs don't usually move like this on their own. They're the quiet remnants of dead stars cooling slowly over billions of years. But when astronomers tracked this one's path, they noticed something bizarre. Its position in the sky shifts slightly over time, as if an unseen hand is nudging it. The only explanation, gravity from a hidden companion. The problem, whatever's out there isn't emitting light, radio waves, or even heat. It's a ghost in the machinery of the cosmos. So what could it be? The first suspect is a black hole. Not the monstrous supermassive ones at galaxy centers, but a smaller, stellar mass black hole, the kind left behind when a massive star collapses. These dark remnants are infamous for their gravity, strong enough to bend light and warp space. But here's the catch. A black hole this close to a white dwarf should be feeding on its companion's material, creating detectable X-rays or jets. Yet WD-1856+534's surroundings are eerily silent. No telltale radiation, no glowing disk, just nothing. Next up, a neutron star. These ultra-dense cores of exploded stars are barely wider than a city but pack more mass than the sun. Some neutron stars, especially older ones, cool down and stop emitting much light, earning them the nickname Black Widow pulsars. But even these faded remnants usually betray their presence through faint radio pulses or gravitational ripples. In this case, not a single signal has been found. It's as if the companion has perfected the art of cosmic hide and seek. Then there's the wild card, something stranger. Could it be a rogue planet dozens of times heavier than Jupiter, drifting unseen through the darkness? Or more tantalizing, a primordial black hole, a hypothetical leftover from the Big Bang itself? These ancient objects, if they exist, would be invisible windows into the universe's earliest moments, but proving their presence is like searching for a shadow in a pitch-black room. What makes this mystery so compelling is its implications. If the companion is a black hole or neutron star, it challenges our understanding of how binary systems form and evolve. If it's something entirely new, it could rewrite the textbooks. Either way, WD-1856+534 is a reminder that the universe still holds secrets in plain sight, or in this case, just out of sight. Coming up next, we'll explore a white dwarf racing across the galaxy at impossible speeds. The cosmic whispers of LP40-365 might just be the aftermath of a stellar explosion that defies all expectations. Now picture a white dwarf that didn't just fade quietly into the cosmic background, it's a runaway. LP40-365 isn't just moving fast. It's racing through the galaxy at speeds that make astronomers double-check their calculations. Over 1,000 kilometers per second, fast enough to escape the Milky Way entirely. But what's even stranger, it's singing. Faint, ghostly radio whispers trail behind it, signals that shouldn't exist for a star like this. Most white dwarfs are the calm leftovers of stars like our Sun, cooling slowly over billions of years. But LP40-365 is different. Its speed suggests it survived a supernova explosion, a cosmic catastrophe that should have obliterated it. Even more baffling, its composition. This star is packed with odd elements like neon, magnesium, and silicon, materials usually forged in the heart of a supernova. It's as if the star was blasted from the inside out, yet somehow held itself together. So how did this happen? One theory is a partial supernova. Imagine a star's core detonating with just enough force to kick the outer layers into space but leaving the white dwarf intact. It's like a grenade going off in your hand, but instead of losing the hand, you're thrown across the room, bruised but alive. The energy from that explosion would explain the star's insane speed. But here's the catch, partial supernovae are hypothetical. No one's ever confirmed they exist. LP40-365 might be the first evidence. Then there's the radio whispers. White dwarfs aren't known for emitting radio waves, especially not faint, pulsing ones like this. One possibility, a magnetic powerhouse. If the star's magnetic field is tangled or unstable, it could generate these signals as it plows through interstellar gas. Another idea, a hidden companion. Maybe a neutron star or black hole is trailing the white dwarf, their interaction sparking the radio noise. But just like WD-1856+534's invisible partner, no such object has been detected. The real shocker, ejection models don't account for this. When stars go supernova, they're supposed to either explode completely or collapse into a neutron star or black hole. A white dwarf surviving and getting flung across the galaxy breaks the rules. Some scientists suggest it was part of a binary system where one star's explosion sent the other careening. Others wonder if it's evidence of an entirely new kind of stellar death. What makes LP40-365 so thrilling is its defiance. It shouldn't exist. It shouldn't move this fast. It definitely shouldn't be whispering to us in radio waves. Yet here it is, a cosmic rebel forcing us to rethink how stars die. Up next, we'll unravel another enigma, a white dwarf with a spectral signature that looks like it's wearing a disguise. The double-peaked emission of GD394 might be hiding more than just atmospheric quirks. Now, let's turn our attention to a white dwarf that seems to be playing a cosmic game of disguise. GD394 doesn't just glow, it flickers in a way that has astronomers scratching their heads. Its light signature isn't smooth or uniform. Instead, it splits into two distinct peaks like a mountain with twin summits. This double-peaked emission is bizarre because white dwarfs by nature are supposed to be symmetrical. So what's causing this star to look so lopsided? One leading theory points to an uneven atmosphere. Imagine a white dwarf with one side burning hotter or denser than the other, like a campfire with a breeze blowing all the flames to one side. This imbalance could distort the light we see, creating those dual peaks. But here's the puzzle. White dwarfs are incredibly dense, with gravity so strong it should smooth out any atmospheric quirks in a matter of hours. So why does GD394's asymmetry persist? Some researchers suggest powerful magnetic fields could be pinning portions of its atmosphere in place, preventing it from evening out. If true, this star's magnetic grip would need to be far stronger than anything we've seen before, raising even more questions. Then there's the accretion angle. Could GD394 be stealing material from a hidden companion like a cosmic thief? If gas from another star is funneling onto the white dwarf unevenly, say, hitting one side more than the other, it might explain the split peaks. But here's the catch, no companion star has been detected. Even more confusing, the spectral lines don't quite match the typical fingerprints of accretion. They're missing key elements like the telltale signs of hydrogen or helium rain falling onto the star's surface. Stellar winds offer another possible explanation. Perhaps GD394 is blasting material into space in an uneven outburst, creating a shroud that distorts its light. But stellar winds from white dwarfs are usually weak and steady, not erratic enough to produce such a sharp, double-peaked signal. Plus, if winds were the culprit, we'd expect to see other clues like shifting spectral lines over time. Yet GD394's twin peaks remain stubbornly consistent. The real intrigue lies in what this star isn't doing. It's not pulsing like WD-1145+017. It's not flaring like ZTF J0139+5245. It's not even whispering in radio waves like LP40-365. Instead, it's sitting there, quietly defying expectations with a light signature that looks like no other. This subtlety makes GD394 a masterclass in cosmic mystery, the kind that doesn't shout its secrets but waits for us to piece them together. Up next, we'll dive into a white dwarf that flickers like a faulty light bulb. The rapid ultraviolet swings of WD-1054-226 aren't just erratic. They're unlike anything else in the known universe. Let's shift our gaze to a white dwarf that behaves less like a steady cosmic beacon and more like a flickering candle in the wind. WD-1054-226 doesn't just shine, it stutters, with its ultraviolet light blinking unpredictably, sometimes surging or dimming in a matter of minutes. This isn't the slow, rhythmic pulsing of older white dwarfs. It's rapid, erratic, and utterly perplexing. Imagine trying to read by a light bulb that brightens and dims at random. That's the puzzle astronomers face when observing this star. So what's causing this bizarre flicker? One compelling idea revolves around orbiting debris. Picture a chaotic ring of shattered asteroids or comets circling the white dwarf, their fragments clumping and dispersing as they spiral inward. If these clouds of dust pass between the star and Earth, they could block UV light in patchy, unpredictable ways. But here's the catch. Most debris disks around white dwarfs create steady, gradual dimming, not the lightning-fast changes seen here. For WD 1054-226, the debris would need to be exceptionally close to the star, almost skimming its surface to explain the speed of the flickering. That raises another question. How could such fragile material survive the star's crushing gravity and scorching heat without vaporizing instantly? Another possibility points to atmospheric instabilities. White dwarfs are known for their stable, layered atmospheres, but what if this one is different? Think of it like a pot of water on the verge of boiling. Tiny bubbles of gas or magnetic disturbances could erupt unpredictably, causing localized bright spots or dimming. Some researchers speculate that pockets of heavier elements like oxygen or neon might sink and rise in turbulent waves, briefly altering how UV light escapes the star. But again, the speed of these changes is the stumbling block. Most atmospheric shifts in white dwarfs unfold over hours or days, not minutes. For this theory to hold, WD 1054-226 would need a bizarre, ultra-dynamic atmosphere unlike any we've catalogued. Then there's the wild card, magnetically driven flares. We know some white dwarfs have powerful magnetic fields that can twist their atmospheres into knots. Could sudden magnetic reconnection, the same process that triggers solar flares, be launching bursts of UV light? It's plausible, but most magnetic flares produce X-rays or visible light, not the isolated UV flickering observed here. Plus, flares usually leave behind telltale signatures in the star's spectrum, and WD 1054-226's date doesn't quite match. What makes this star truly fascinating is its uniqueness. Unlike the pulsating WD 1145+017 or the X-ray bursting GD358, WD 1054-226 doesn't fit any known category. Its flickering isn't just rare, it's singular, defying every template astronomers have for stellar behavior. That's why some scientists wonder if we're seeing not one phenomenon, but a bizarre interplay of several. Maybe debris spiraling inward while magnetic flares erupt while the atmosphere churns. Untangling this mess could redefine how we understand white dwarfs altogether. Up next, we'll uncover a white dwarf pair that should be screaming in X-rays, but instead they're eerily silent. The merger of ZTF J0139+2645 is breaking all the rules, and no one knows why. Now, let's turn our attention to a cosmic event that should have been deafening, but instead it's shrouded in silence. Meet ZTF J0139+2645, a pair of white dwarfs locked in a violent dance of merging. Normally, when two dense stellar corpses collide, they unleash a storm of X-rays, screaming their fury across the universe. But here's the twist: this duo is eerily quiet. Where are the X-rays? Astronomers expected a fireworks show, but all they've found is a baffling hush. So, what's muffling this cosmic scream? One leading theory points to shock absorption. Picture two white dwarfs spiraling toward each other, their surfaces churning with unimaginable heat and pressure. As they merge, the sheer force of the collision should send shockwaves racing through their interiors, superheating material and blasting out X-rays. But what if something's soaking up that energy before it can escape? Some researchers propose that thick layers of turbulent plasma, A soup of charged particles might be acting like a cosmic sponge, absorbing the X-rays and converting them into less detectable forms of energy. It's like throwing a pebble into a pond, only for the ripples to vanish before they reach the shore. Then there's the possibility of exotic plasma physics at play. White dwarfs are already extreme environments, but a merger cranks everything up to 11. Under these conditions, the usual rules of electromagnetism and particle behavior might break down. For instance, magnetic fields could become so twisted that they trap X-rays entirely, or the plasma might form strange, dense structures that scatter the light into oblivion. Think of it as a hall of mirrors for high-energy radiation. The X-rays bounce around so much they never make it out. This wouldn't just explain the silence, it would hint at physics we've never observed before. But the plot thickens when we consider the timing. Merging white dwarfs are supposed to be messy, chaotic affairs, with X-ray outbursts flaring up as the stars tear each other apart. Yet as ZTF J0139+5245's merger seems oddly synchronized, as if some unseen force is smoothing out the violence. Could tidal forces, the gravitational tug of war between the two stars, be stretching the X-ray emitting region so thin that the radiation simply dissipates? Or is there an unseen third object, like a rogue planet or black hole, quietly siphoning off energy? What makes this merger so fascinating is the sheer defiance of expectations. Every model of white dwarf collisions predicts X-rays, but this pair is rewriting the script. It's as if the universe is reminding us that even the most violent events can unfold in whispers. Solving this mystery could revolutionize our understanding of stellar deaths, plasma physics, and even the fate of binary star systems. Coming up next, we'll decode a white dwarf whose pulsations look eerily like Morse code. PG1159-035 isn't just ticking, it's speaking in a language we're only beginning to understand. Now, imagine a white dwarf that doesn't just flicker, it communicates. PG1159-035 isn't your typical silent stellar remnant. Instead, it pulses with a rhythm so precise, it's as if the star is sending signals straight out of a cosmic telegraph. These aren't random flickers, they follow intricate patterns, rising and falling in a sequence that eerily resembles Morse code. But what's causing this celestial messaging, and is the universe really trying to talk to us? At the heart of this mystery are gravity mode oscillations, or G modes for short. Picture the white dwarf's interior like a vast ocean, with waves constantly rippling through its dense layers. These aren't water waves, of course, but vibrations driven by gravity itself. As material inside the star shifts and settles, it creates pulses that travel outward, subtly altering the star's brightness in a predictable rhythm. PG1159-035's pulsations are so regular that astronomers can almost set their clocks by them. But here's the catch. The patterns are far more complex than anything our current models can fully explain. It's like listening to a symphony where every instrument is playing in perfect harmony, yet we've only just begun to decipher the sheet music. Then there's the wild card subsurface convection anomalies. White dwarfs are supposed to cool down steadily, their outer layers becoming more uniform over time. But this star defies expectations. Beneath its surface, turbulent pockets of hot plasma may be churning unpredictably, like bubbles in a boiling pot. These convection zones could be distorting the pulsations, adding unexpected twists to the star's rhythmic signals. Imagine a drummer whose beats speed up or slow down because the drum itself keeps changing shape. That's the kind of chaos astronomers suspect might be at play here, and it could rewrite what we know about how white dwarfs evolve. What makes PG1159-035 truly fascinating is how its pulsations mirror real-world coding systems. The intervals between its pulses aren't random, they cluster in distinct groups, almost like letters in an alphabet. Some researchers have even joked that if we translated the patterns into sound, they'd sound like a radio transmission. Of course, the idea of an actual alien message is far-fetched, but the parallels are undeniably eerie. This star's behavior forces us to ask, could natural processes alone create such organized complexity, or is there something deeper we're missing? The implications stretch beyond a single white dwarf. If we can crack the code of PG 1159-035, we might unlock secrets about the internal structure of all white dwarfs. These pulsations are like X-rays for stellar interiors, revealing details about density, composition, and even magnetic fields that would otherwise stay hidden. Plus, understanding G-modes could help us predict how other stars, including our own sun, might behave in their final stages. It's a cosmic puzzle with stakes much higher than just one star's strange signals. As we unravel this celestial cipher, another enigma waits in the wings. Up next, we'll confront a white dwarf whose dimming defies all logic. Could dark matter be casting a shadow where none should exist? Now, shifting our gaze to a different kind of cosmic mystery, we encounter a white dwarf that seems to vanish before our eyes. WD 1425+540 doesn't just flicker or pulse, it dims in a way that defies every conventional explanation. Conventional wisdom tells us that when a star dims, it's usually due to something blocking its light, dust, debris, or maybe a planetary companion passing in front. But WD 1425+540's dimming doesn't fit any of these scenarios. Instead, its light fades in a pattern so unusual, some scientists wonder if we're seeing the shadow of something far stranger, dark matter. The star's dimming episodes are erratic, with no clear periodicity or predictable cause. Unlike the rhythmic pulsations of PG 1159-035, these dips in brightness seem almost arbitrary, as if an invisible hand is occasionally blotting out the star's glow. Traditional extinction theories like interstellar dust clouds or orbiting debris fail to explain the observations. Dust would scatter light in predictable ways, and debris would leave chemical traces in the star's spectrum. But here, there's no dust, no debris, no telltale signs of anything conventional. That's where dark matter enters the conversation. Dark matter, that elusive substance making up roughly 27% of the universe, doesn't emit, absorb, or reflect light. We only know it exists because of its gravitational effects on galaxies and galaxy clusters. But could it also interact with stars in ways we've never seen? One radical hypothesis suggests that dense clumps of dark matter, so-called dark matter halos, might occasionally pass in front of WD 1425+540, absorbing just enough starlight to cause the observed dimming. It's a stretch, but not impossible. If true, this would be our first direct hint that dark matter isn't just a cosmic placeholder. It's something that tangibly, if subtly, alters the light of stars. Of course, not everyone is convinced. Skeptics argue that the dimming could still be caused by more mundane, yet undiscovered, astrophysical phenomena. Maybe the star has a peculiar magnetic field that traps and releases clouds of ionized gas in irregular bursts. Or perhaps there's an undetected companion, a brown dwarf or rogue planet orbiting in a chaotic path that occasionally eclipses the white dwarf. These explanations are less exotic, but they're also incomplete. None fully account for the star's unique dimming profile, leaving the dark matter hypothesis tantalizingly on the table. What makes this mystery especially compelling is how it blurs the line between the known and the unknown. Dark matter is already one of cosmology's biggest puzzles, and if WD 1425+540's dimming is indeed tied to it, the implications are staggering. We're not just talking about understanding one star, we're talking about unlocking a whole new way to detect and study dark matter. Imagine if white dwarfs scattered across the galaxy could serve as natural dark matter detectors, their flickers revealing the invisible architecture of the universe. For now, though, the shadow over WD1425+540 remains unexplained. Whether it's dark matter or something equally bizarre, this star challenges us to think beyond the textbook. And as we peel back the layers of this enigma, another cosmic oddity beckons, one where light doesn't just vanish but lingers in echoes from a violent past. Now turning our attention to a cosmic phenomenon that seems to rewrite its own history, we arrive at the enigmatic white dwarf G299.2-2.9. Unlike most stellar remnants, this one doesn't just sit quietly in space, it's surrounded by ghostly echoes of light, as if the star is replaying its own violent past. These delayed light echoes aren't just a curiosity, they're a clue, hinting that this white dwarf might have once been something far more explosive, a supernova hiding in plain sight. Light echoes occur when a star's explosive outburst, like a supernova, sends a flash of light racing through space. That light hits nearby clouds of dust and gas, scattering in all directions. Some of it reaches us immediately, but some takes a longer path, bouncing off interstellar material before finally arriving at Earth years or even decades later. It's like hearing an echo in a canyon long after the original shout. In the case of G299.2-2.9, these echoes aren't just faint whispers, they're bright, unmistakable signatures of a cataclysm that should have torn the star apart entirely. Here's the puzzle. White dwarfs are the quiet end-stage remnants of stars like our Sun, not the progenitors of massive supernova. So how could G299.2-2.9 be linked to such a violent event? The leading theory suggests this white dwarf might have once been part of a binary system where two stars orbited each other closely. If one of those stars was a massive companion, its death throes could have triggered a supernova, leaving behind the white dwarf we see today. Alternatively, the white dwarf itself could have stolen enough material from its partner to grow unstable, igniting a smaller-scale explosion known as a Type 1, a supernova, though this would typically obliterate the dwarf entirely. Neither scenario neatly explains why the star survived or why its echoes persist with such eerie clarity. The echoes themselves add another layer of intrigue. By studying their timing and brightness, astronomers can reconstruct the original supernova's light curve, essentially rewinding the cosmic tape to see how the explosion unfolded. What they've found is baffling. The echoes suggest a supernova unlike any we've catalogued. The energy output, the speed of the blast, even the chemical fingerprints in the surrounding nebula, they all deviate from known models. Some researchers propose this could point to an entirely new class of supernova, one where the star doesn't just explode, but undergoes a series of violent spasms, leaving behind a damaged but intact remnant. Others argue the white dwarf might not be the remnant at all, but a bystander caught in the aftermath of another star's demise. Then there's the broader implication. If G299.2-2.9 truly is a supernova survivor, it challenges our understanding of how stars die. Conventional wisdom says supernovae are final, destructive events, no ashes, no remnants, just scattered debris. But if a white dwarf can emerge from such an explosion, it means some stars might weather these cosmic storms in ways we never imagined. This could rewrite the rules of stellar evolution, suggesting that under rare conditions, even the most violent deaths aren't always the end. For now, the echoes of G299.2-2.9 continue to ripple through space, carrying secrets from a past we're only beginning to decipher. Whether they reveal a new kind of supernova or a celestial illusion, one thing is certain: this white dwarf is more than a quiet ember. It's a cosmic storyteller, and we're just learning how to listen. And as we unravel its tale, another mystery awaits, one where time itself seems to bend around a white dwarf's enigmatic glow. Now imagine a star that doesn't just shine, it seems to remember. This is the bizarre case of WDJ 0914+1914, a white dwarf that emits signals with an eerie delay, as if it's replaying its own past. These aren't ordinary pulses of light or radio waves, they're emissions that arrive late, out of sync with any known stellar activity. It's like the star is whispering secrets from a time that's already passed, leaving astronomers scrambling to decode what could possibly cause such a cosmic déjà vu. The mystery centers on the star's light curves, the patterns of brightness changes over time. Normally, white dwarfs flicker or pulse in predictable ways, tied to their rotation or internal processes. But WDJ 0914+1914 behaves differently. Its emissions don't match its current state. Instead, they seem to echo events that happened years earlier. Imagine tapping a piano key and hearing the note play a minute later. That's the level of strangeness we're dealing with here. One leading explanation involves gravitational lensing, the bending of light around massive objects. If there's an unseen structure, like a black hole or dense dust cloud between Earth and the white dwarf, it could warp spacetime enough to delay some of the star's light. Think of it as a cosmic detour, photons taking a longer path around the obstacle before finally reaching us. But here's the catch: lensing usually creates multiple images or smears the light, not a clean, time-shifted copy. WDJ 0914+1914 signals are too crisp, too precise for typical lensing effects. That's where things get even wilder. Some theorists suggest this could be a rare glimpse of quantum spacetime phenomena, physics so extreme it warps our understanding of cause and effect. In certain quantum gravity models, spacetime isn't smooth and continuous but granular, like a mosaic of tiny pixels. If the white dwarf's light interacts with this frothy structure, it might emerge scrambled or delayed, as if passing through an invisible sieve. It's a fringe idea, but the signals from this star are fringe enough to justify considering it. There's another twist: the delays aren't random. They follow a rough pattern, almost like a fading echo. This has led a handful of researchers to propose the white dwarf might be entangled with another object, a neutron star or even a primordial black hole through a wormhole or some exotic spacetime link. In this scenario, emissions could leak through the connection, arriving out of sequence. Again, it's speculative, but when conventional physics falls short, the door opens to extraordinary possibilities. What makes WDJ 0914+1914 especially tantalizing is the potential ripple effect on astrophysics. If the delays stem from new physics, they could help bridge gaps in our understanding of gravity, quantum mechanics, or even dark matter. Alternatively, if the cause is more mundane, say, an unusually shaped debris disk warping the star's emissions, it would still push the boundaries of how we model stellar environments. Either way, this white dwarf forces us to question whether we're seeing the star as it is now, or as it once was, its light trapped in a celestial time warp. As we grapple with these ideas, another enigma looms on the horizon. The cosmos is full of puzzles, and the next one might just redefine how we perceive the fabric of reality itself. Now, shifting our gaze to another cosmic conundrum, let's unravel the baffling behavior of HLX-1, a white dwarf that defies expectations in the most unexpected way. Normally, when a star brightens in one part of the spectrum, it does the same in others, like turning up the volume on both bass and treble. But HLX-1 flips this logic on its head. Its X-ray and optical brightness move in opposite directions. When one surges, the other dips, creating a celestial seesaw that has astronomers utterly stumped. This anti-correlation isn't just a minor oddity, it's a glaring anomaly. Picture a firework that dims as it explodes, or a light bulb that grows darker the more energy you feed it. That's the level of contradiction we're dealing with here. So, what could possibly cause such a bizarre inverse relationship? One leading theory points to jet precession, a phenomenon where powerful jets of particles, often launched by accretion disks, wobble like a spinning top. If these jets periodically point toward or away from Earth, They could alternately amplify X-rays when aimed at us and scatter optical light when tilted away, creating the observed seesaw effect. It's like a cosmic lighthouse whose beam sometimes blinds you with X-rays and other times hides its visible glow. But there's a twist. Jet precession usually follows predictable cycles, while HLX-1's brightness shifts are erratic, almost capricious. This has led some researchers to suspect disk instabilities, violent turbulence in the white dwarf's accretion disk. Imagine a whirlpool that suddenly churns faster, flinging material inward in fits and starts. These chaotic surges could heat the disk's inner regions, boosting X-rays while starving its outer edges, dimming optical light, or vice versa. It's a delicate balancing act, and HLX-1 seems to be teetering on the edge. The plot thickens when we consider the star's environment. HLX-1 orbits near a massive companion, likely a neutron star or black hole whose gravity could be warping the disk unevenly. This might trigger shadowing effects, where dense clumps of material intermittently block optical light while allowing X-rays to slip through. Think of it as a cosmic game of peekaboo, where the rules keep changing without warning. What makes HLX-1 especially tantalizing is its potential to rewrite how we understand accretion physics. Most models assume a harmonious link between different wavelengths, but this star screams otherwise. If its behavior stems from some exotic disk geometry or unseen magnetic fields, it could force us to rethink how energy is distributed in these extreme systems. Alternatively, if the answer lies in a previously unnoticed interaction between the white dwarf and its companion, it might reveal new facets of binary star dynamics. As we piece together this puzzle, one thing is clear. HLX-1 isn't just an outlier, it's a rebel challenging the textbooks with every flicker. And in that defiance, it offers us a rare chance to glimpse the unscripted chaos of the universe. Up next, we'll confront an even deeper mystery: signals that vanish into the void, leaving no trace behind. Now, as we arrive at the final enigma in our cosmic journey, we encounter something truly baffling: Gaia's orphan signals. These are strange blips of light captured by the Gaia Space Telescope, emissions that don't seem to belong to any known white dwarf or even any recognizable celestial object. Imagine scanning the night sky with the most advanced tools humanity has ever built, only to find flashes of light with no clear parent, no star, no galaxy, nothing. That's the mystery we're facing here. At first glance, it's tempting to dismiss these signals as mere glitches, the kind of electronic noise that inevitably creeps into even the most precise instruments. But Gaia is no ordinary telescope. It's one of the most sophisticated observatories ever launched, designed to map the positions and movements of over 1 billion stars with unparalleled accuracy. For it to record signals that don't match any known object raises eyebrows across the scientific community. So, what could these orphan signals actually be? One possibility is that they're fleeting cosmic events, brief explosions or collisions happening in the depths of space, too faint or distant for follow-up observations. Picture a firefly blinking in a pitch-black forest. By the time you turn to look, it's already gone. Some researchers speculate these could be tidal disruption events, where a star is torn apart by a black hole, releasing a burst of energy that vanishes almost as quickly as it appears. Others suggest they might be rare supernova variants, detonating in ways we haven't yet catalogued. But here's where things get even stranger. Some of these signals reappear in the same spot, flickering on and off in patterns that don't match any known astronomical phenomena. This rules out one-time events and points to something more persistent, perhaps objects that exist outside our current understanding of stellar physics. Could these be white dwarfs cloaked in exotic matter, or even entirely new classes of celestial bodies? The data doesn't yet provide a clear answer, and that's what makes this so thrilling. Then there's the chance, however slim, that these signals aren't natural at all. When unexplained emissions crop up with no obvious source, it's hard not to wonder if we're seeing some form of artificial activity. Before you jump to aliens, though, let's ground this in science. And this is a big if, these signals were engineered, they'd likely exhibit telltale signs like unnatural regularity or encoding. Gaia's orphans don't fit that bill, at least not yet. But the mere possibility keeps the door open for radical explanations, and scientists are rightfully cautious about ruling anything out prematurely. The real puzzle lies in how to study these ghosts of the cosmos. Without a visible counterpart, astronomers can't train other telescopes on them for closer inspection. It's like trying to solve a murder mystery with only half the clues. Future missions like the upcoming Vera Rubin Observatory might help by scanning the sky with even greater sensitivity, potentially catching these phantoms in the act. Until then, Gaia's orphans remain one of the most frustrating and tantalizing mysteries in modern astronomy: signals without a source, questions without answers. What makes this final enigma so compelling is its sheer defiance of explanation. It's not just another oddity in a catalogue of stellar quirks, it's a blank spot on the map, a reminder of how much we still don't know. Whether these signals are cosmic glitches, unknown objects, or something beyond our current imagination, they underscore a humbling truth: the universe always keeps a few cards close to its chest. And as we close this chapter on white dwarf mysteries, we're left with one enduring thought: the greatest discoveries often begin with the words, "Wait, what is that?" Now, stepping back from the individual mysteries, let's zoom out to see the bigger picture these signals paint, a portrait of astrophysics itself being pushed to its limits. What do these 25 unexplained phenomena tell us about the gaps in our understanding of the universe? Quite a lot, as it turns out. Each of these white dwarf signals isn't just a curiosity. It's a crack in the foundation of what we thought we knew about stars, gravity, and even the fabric of space-time. Take stellar evolution for starters. White dwarfs are supposed to be the quiet final act of stars like our Sun, slowly cooling into cosmic embers. But the erratic pulsations of stars like WD 1145+017, or the sudden temperature spikes of WD J2356-209 throw that tidy narrative into chaos. These behaviors suggest there's more to a white dwarf's life cycle than we've accounted for, perhaps unseen interactions with hidden companions, or even exotic physics in their ultra-dense cores. It's as if these stars are whispering, "You've only scratched the surface." Then there's quantum physics, which gets dragged into the spotlight by signals like the repeating fast radio bursts from J1912-4410. Fast radio bursts are usually the domain of neutron stars, yet here's a white dwarf mimicking them. Could this mean white dwarfs harbor magneta like magnetic fields, or that our classification of compact objects is too rigid? Even more perplexing are the ghostly infrared glows and phantom dust clouds around stars like WD 0806-661 and G29-38. These could hint at quantum interactions between stellar material and dark matter, or entirely new states of matter we haven't yet dreamed up. Cosmology isn't spared either. The gravitational wave whispers from RX J0806.3+1527, or the dark matter-like dimming of WD 1425+540, force us to reconsider how mass and energy weave the cosmic web. Are we missing a hidden component of the universe, something beyond dark matter and dark energy? And let's not forget Gaia's orphan signals, emissions with no identifiable source. If they're not instrumental glitches, they could imply entire classes of objects or phenomena that don't fit our current maps of the cosmos. The beauty and frustration of these mysteries is how they resist easy fixes. No single tweak to our models can explain all 25 signals. That's why researchers are attacking the problem from every angle. Teams are refining simulations to account for chaotic stellar mergers, while others are developing new detectors to spot faint gravitational waves or elusive particles. Projects like the James Webb Space Telescope and the upcoming Laser Interferometer Space Antenna, or LISA, are poised to peer deeper into these enigmas, armed with sharper eyes and broader wavelength. But perhaps the most profound implication is this: these signals remind us that the universe is far stranger than our textbooks allow. Every time we think we've got it figured out, a white dwarf flares, pulses, or vanishes in a way that leaves us baffled. And that's exactly what makes astrophysics so exhilarating. It's not just about filling gaps, it's about discovering that the gaps are wider and weirder than we ever imagined. The next breakthrough might not come from confirming what we suspect, but from stumbling onto something we didn't even know to suspect. So where does that leave us? In the best possible place, on the edge of discovery. With each unexplained signal, we're handed a new puzzle piece, and the growing sense that the full picture is nothing like we expected. The universe, it seems, still has plenty of surprises up its sleeve. Now, let's take a playful detour into one of the most tantalizing questions these mysteries raise. Could any of these signals be more than just cosmic quirks? Could they, in some wild twist, be signs of intelligence beyond Earth? It's a question that's as old as astronomy itself, and white dwarfs have now waded into the debate. Let's be clear, the scientific consensus is that these signals almost certainly have natural explanations. Occam's razor, the idea that the simplest solution is usually the right one, cuts heavily in favor of astrophysical phenomena over alien megastructures or interstellar Morse code. After all, the universe is vast and full of processes we're still unraveling. Take Boyajian's star with its bizarre dimming patterns. While it's fun to imagine a Dyson swarm built by an advanced civilization, the more plausible answer involves swarms of comets or dusty debris. Similarly, the repeating fast radio bursts from J0139+5445, far likelier to stem from extreme magnetic activity than extraterrestrial radio beacons. That said, dismissing the idea entirely would miss the point. The allure of the unknown is what drives science forward. History is littered with discoveries initially brushed off as too strange to be real until they weren't. Pulsars, for instance, were nicknamed LGM, little green men, when first detected because their precise pulses seemed artificial. Of course, they turned out to be rapidly spinning neutron stars, but that moment of uncertainty highlights how even seasoned scientists can't help but wonder. So where does that leave the more exotic white dwarf signals? Consider the cosmic Morse code of PG 1159-035 with its intricate pulsation patterns. Could it be a beacon? Probably not, but the fact that it mimics coded messages is a delightful coincidence that fuels speculation. Or the orphan signals in Gaia's data, which defy identification. While most are likely glitches or undiscovered stellar phenomena, the slim chance there's something entirely new, artificial or otherwise, keeps astronomers digging. The truth is, the line between natural and artificial blurs when we confront the limits of our knowledge. A sufficiently advanced civilization might harness physics we haven't even theorized yet, making their technology indistinguishable from natural phenomena. That's why projects like SETI, the search for extraterrestrial intelligence, take these possibilities seriously, even as they prioritize rigorous analysis. They're not just chasing little green men, they're asking, what don't we know and how might intelligence hide within it? In the end, the odds are slim, but the stakes are cosmic. If even one of these signals defied natural explanation, it would rewrite humanity's place in the universe. Until then, the debate serves a different purpose. It keeps us questioning, imagining, and most importantly, looking up. Because whether the answer is aliens or a new law of physics, the universe has clearly saved its best surprises for those willing to wonder. Now, let's turn our gaze to the future, because the mysteries of white dwarfs won't solve themselves. Luckily, a new generation of telescopes and space missions is gearing up to peer deeper into these cosmic puzzles than ever before. These aren't just incremental upgrades, they're game changers designed to tackle the very enigmas we've been exploring. First up, the James Webb Space Telescope, already revolutionizing astronomy, is just getting started. Its infrared eyes are perfect for dissecting the ghostly glow around stars like WD 0806-661, where unexplained infrared excesses hint at debris disks or cold companions. Webb's sensitivity could finally tease apart the composition of these elusive features, revealing whether they're made of crushed planets, interstellar dust, or something entirely unforeseen. And for white dwarfs with bizarre atmospheric chemistry like ZTF J0139+5245, with its rogue oxygen and neon Webb spectrographs can trace the origins of these elements, testing if they're scars from exotic supernova or interstellar pollution. But Webb isn't flying solo. Enter LISA, the Laser Interferometer Space Antenna, slated to launch in the next decade. While Webb studies light, LISA will eavesdrop on spacetime itself, detecting gravitational waves. This is huge for white dwarfs like RxJ 0806.3+1527, whose faint gravitational whispers might finally be audible. LISA could uncover whether these waves stem from tight binary systems, hidden mergers, or even exotic objects like primordial black holes lurking nearby. And for white dwarfs with erratic spins like UV J0317-855, LISA might catch the gravitational tremors of internal quakes or phase transitions, offering clues to their turbulent interiors. Then there's the Vera C. Rubin Observatory, set to scan the entire southern sky every few nights. Its relentless gaze is ideal for catching white dwarfs in the act of mischief, like the sudden flares of ZTF J0139+5245 or the flickering UV light of WD 1054-226. Rubin's time domain surveys could reveal patterns in these outbursts, exposing whether they're triggered by asteroids, magnetic storms, or unseen companions. And for Gaia's orphan signals, those mysterious blips with no known stellar source, Rubin's precision might finally match them to a parent star or confirm they're something entirely new. Meanwhile, advanced radio telescopes like the Square Kilometre Array will listen in on white dwarfs like LHS 3250, whose radio emissions defy expectations. With sensitivity 50 times greater than current arrays, it could pinpoint whether these signals come from interacting binaries, magnetospheric fireworks, or dare we say structures we haven't imagined yet. Even SETI tools are evolving. Next-gen optical and radio searches will scan white dwarf signals for technosignatures, not because they expect aliens, but because ruling out the impossible is how science progresses. The beauty of these missions lies in their synergy. Webb's chemical fingerprints, LISA spacetime ripples, Rubin's cinematic sky scans, and SK's radio whispers will cross-examine these mysteries from every angle. What emerges could be as simple as a new type of stellar debris, or as profound as a rewrite of how stars evolve. Either way, the next decade promises something rare answers. So stay tuned. The universe has spent centuries whispering its secrets. Now, we're finally building the tools to shout back. Now, as we bring our journey through these cosmic puzzles to a close, let's take a moment to reflect on just how extraordinary these 25 unexplained signals from white dwarfs truly are. From the erratic pulsations of WD 1145+017 to the ghostly whispers of Gaia's orphan signals, each one has challenged our understanding of the universe in ways we never expected. These aren't just anomalies, they're invitations to explore, to question, and to rethink what we know about the life and death of stars. Think about it. A star like KIC 8462852, with its bizarre dimming patterns, had scientists debating everything from alien megastructures to colossal dust clouds. ORGD 358, blasting out X-rays on no discernible schedule, defying every model of stellar behavior. And who could forget LHS 3250, a white dwarf sending radio signals like a cosmic radio station with no clear DJ. These mysteries remind us that space isn't just vast, it's alive with surprises waiting for us to piece them together. But here's the most exciting part: we're not just passive observers. With tools like the James Webb Space Telescope, LISA, and the Vera-C, Rubin Observatory coming online, we're on the brink of breakthroughs that could rewrite textbooks. Maybe we'll finally crack the code behind the repeating fast radio bursts of J0139+4410, or unravel why SDSS J0139+2645, emerging white dwarf pair, refuses to emit the X-rays we'd expect. Every unanswered question is a door waiting to be opened. So what's next? That's where you come in. Whether you're a seasoned stargazer or someone who just loves a good cosmic mystery, the universe has a way of speaking to those who listen. Maybe tonight's the night you step outside, look up, and wonder about the secrets hidden in the glow of distant stars. Or perhaps you've got a wild theory about one of these signals. Drop it in the comments below. Science thrives on curiosity, and who knows, your idea might just spark the next big discovery. If these mysteries have left you as captivated as they've left astronomers, don't let the journey end here. Hit that subscribe button so you won't miss our deep dives into other cosmic enigmas, because trust me, the universe has plenty more up its sleeve. And if you've enjoyed this tour through the unknown, give this video a like to help others discover it too. As we sign off, remember, the universe isn't just stranger than we imagine, it's stranger than we can imagine. So keep looking up, keep asking questions, and above all, stay curious. The next great cosmic revelation might be just one observation away. Until then, happy stargazing.